All right, y'all, welcome back to my DP chemistry curriculum. Today we're on lesson 20, structure 1.5.2. We're talking about real gases, how they deviate from ideal gas model, and specifically at low temperature and high pressure. And we'll figure out why that makes sense. Uh, there's also one more way they deviate, and we'll talk about it as we continue into real gases. So we discussed earlier about ideal gases. These are generally gases that we refer to. We have a couple assumptions that we make about them, assumptions on how they interact. Now, these help us when we describe chemical phenomena. If we have some gases in a container and these gases are bouncing off the walls, maybe bouncing into each other or whatever. Now, what happens if we made that container bigger and we expanded it to maybe double its size? What happens if we put some fire under it and heat it up? And we'll be able to describe those using the ideal gas. But the problem with ideal gases is not all real gases act like this. There is something called real gases, which are all the gases that we deal with in the normal world, and they deviate from ideal behavior. So we're going to discuss why they deviate from those behaviors and how we can kind of deal with that. So from the intro, we see that one of the big things is high pressure. Now, particles have these attractive forces that bring them together. And in an ideal situation, we say, well, these don't really exist. They're negligible. Well, there's ways we can make them no longer negligible. If we have high pressure, the particles are forced together. We can have high pressure by putting more particles in, forcing them to be in very close quarters, which starts looking more like a liquid or a solid. Now, they're still moving around and bouncing off one another, but they're closer. And when they are closer, these what we call intermolecular forces, attractive forces, can take effect. So by allowing them to get closer together, these forces can start overwhelming. And when these start actually having an effect on the gas behavior, it is no longer ideal and becomes a real gas. The other way we can do this is by slowing them down. Now, the way we can slow them down is with low temperature. If you imagine two magnets racing past each other at 900 kilometers an hour, they only spend so much time in the same space that the attraction between them is negligible. They won't really deflect because they're going so fast. But if you slow these down quite a bit and they're just like crawling, then they'll have a lot more time to interact with one another and attract. So at low temperature, those same intermolecular molecular forces have a larger impact on particle behavior. And we said that is not ideal. Ideal says these forces don't exist, but if they are, that makes these real gases. So those are the two main ways that we can take an ideal gas and make it act more real. So just to write this out, we have ideal and we have real. And in an ideal gas, we want very low pressure, so the particles are far away, and high temperature, so they're moving very fast. In a real gas, that's when we have high pressure, so the particles are very close, and we have low temperature, so the particles are moving very slowly. The last and final aspect of this is something that you may not expect, but it's molar mass of the gas. The reason this is kind of weird is because we mentioned that gases don't really care about how heavy the individual particles are. They all kind of act the same. But this affects something we'll talk about in a few sections down the road about also a third intermolecular force. forces. There's one specifically called LDFs, or London dispersion forces, and you don't need to know about them much yet, but we'll make them clear later. And LDFs, or London dispersion forces, they are based on molar mass. So if it has a large molar mass, that equates to a large force. So basically, if we take two gases, for example, helium and sulfur hexafluoride. Helium has a molar mass of about 4.00 grams per mole, while sulfur hexafluoride is about 146.06 grams per mole. Sulfur hexafluoride will have a much larger attractive force between particles. Therefore, helium would be ideal and sulfur hexafluoride would act real. So that's about it for real gases. I hope this helps and have a great day.